We're going to review the idea of total internal reflection. This is our chapter 26-2 video. And what we have here is, if you look at this first picture, picture A, we have light coming up through the water. The refracted ray bends away from the normal, that's theta 2. And then you also have partial reflection, which is theta 1, that's your reflected ray. Now if you go over to B, what happens is if you change theta 1 to be at such a position that the refracted ray is actually 90 degrees, that theta 1 right there is called the critical angle. That's the angle where the angle of refraction of the light ray is 90 degrees. And then if you come down here and you go if you go beyond the critical angle in this picture C, you get total internal reflection. None of the light coming up to the interface will actually penetrate through into the air. So a few things here. The critical angle is where the angle of refraction is 90 degrees. Total internal reflection occurs when the incident light is beyond the critical angle. And this phenomenon will only occur if you are if the light is going from a high index refraction to a lower index refraction, because you need the light ray to bend away from the normal to go to 90 degrees. Our example of this is right here. We have light coming from the white into the yellow. 1.24 is the index refraction, high index refraction when compared to the 1.0. And I'm going to increase this index refraction. You'll see, oh, there's total internal reflection. When I made the medium have a value of 1.31, that 49 degrees then became the critical angle, or we went beyond the critical angle. So we had total internal reflection occur. Here's an example of why diamonds are so sparkly. What happens is the light comes in. You want the light to come in at an angle beyond the critical angle so that you have total internal reflection, and so that any of the light coming into the diamond actually gets trapped down inside here because it's beyond the critical angle and bounces back out, and then the light comes back up at you, and so the diamond is sparkly, and that's why the diamond is cut at a certain angle. So if you read up here, a diamond cutter wants to cut the diamond so the light stays inside the diamond. The light should bounce back with total internal reflection and make the diamond sparkle. If they cut it incorrectly, you'll see that the light leaks out of the bottom and not very much light will reflect back. Binoculars also use this phenomenon because it's easier to put a prism inside binoculars than to try to place mirrors. So your light comes in and total internal reflection occurs because this 45 degrees is beyond the critical angle. And you can have it work this way, or if you look at this prism over here, the same thing holds true. You can have light come in and then come straight back out. And so if you look at the binoculars here, the light from whatever you're watching comes in. You set up the prism so that the angles are beyond the critical angle. They reflect just like a mirror, and it comes straight back out. What's also nice about this is that the mirror doesn't get pitted and so on. It stays nice and clean, and so this is why binoculars use prisms instead of mirrors to work. Fiber optics is another example of total internal reflection. Fiber optics keep the light inside the glass tube so the light can be transmitted and come out the other end. This light comes in carrying information through the glass optic here, or the optical through these optics, and it carries information. And this is much more efficient than electricity carrying information. A lot of times stereos will use fiber optics to transfer information instead of electricity. Fiber optics is being used more and more to carry information for communications and so on. And here's just an example of a fiber optic flower here. They have light coming up from the bottom, traveling up through this through the glass, and then you see the light come out the other end. Surgeons also use optical fibers to see what's inside a person's knee. For example, here we have a scope going inside a person's knee, and the surgeon is using fiber optics to be able to see inside that knee. So optical fibers have made arthroscopic surgery possible, such as the repair of a damaged knee shown in this photograph. And they can do it with very small cuts into the knee. And so they can go in there and see exactly what's going on using fiber optics. And the tube, the fiber optics, does not have to be straight. It can be bent, and they can see what's going on. So let's try a problem here. It says a beam of light is propagating through diamond and strikes a diamond-air interface at an angle of incidence of 28 degrees. What will the light do at this interface? In other words, will a total internal reflection occur, or will the light transmit through the interface out into the air? Then repeat part A, assuming that the diamond is surrounded by water. So air has an index refraction of 1.0, where water has an index refraction of 1.33. So I'd like you to do both A and B here. Pause the video, try this out, and see if you come up with the right answer. So what you can do first here is find the critical angle for total internal reflection to occur at the diamond air interface. And so you'll use Snell's law. And this is Snell's law just in a different format. But if you use Snell's law to find the critical angle, you end up with 24.4 degrees is the critical angle. And since the 28 degrees is beyond that 24.4 degrees, in other words, it's beyond the critical angle, the light is totally reflected back into the diamond. So total internal reflection occurs. Now for part B, if water surrounds the diamond, let's go ahead and use Snell's law again, find that critical angle. Remember, when you're doing the critical angle, it's you have to use sine of 90. Remember that second angle is 90 degrees. If you had a hard time before, what you do is theta 2 is 90 degrees. And you find this critical angle to be 33.3 degrees. So the angle of incidence of 28 degrees is less than the critical angle of 33.3 degrees, so the light will reflect and also refract through, and the light will go out into the air. So the key here is that you made theta 2 90 degrees. In case you had a hard time following the previous example, what I've done here is I've set up Snell's law, and remember when we were going from diamond. Let's do diamond into water. So we have diamond into water, and we have our light ray coming up. We want to know, at this normal line, what the critical angle is, and that means that the light ray goes right along the interface. So theta 2 is 90 degrees. This is theta 1, the critical angle, and this is theta 2 up here, which equals 90 degrees. So when you come over here, your N1 is diamond, so that's 2.42. Sine of theta 1 is, we're just going to call that the critical angle, equals N2. In this case, it's water, so that's 1.33. In the other case, if it was air, it would have been 1.0. And we put in here the sine of 90 degrees. We know the sine of 90 degrees is 1. So when we go ahead and solve for that critical angle, we ended up with an answer of 33.3 degrees. And this was for part B in that previous answer. If you did part A, you would have put in for N2, you would have put in 1, and you would have ended up with an answer of 24 degrees.